Hello and welcome to the first part in a video series where I'm going to show you how I designed and built this cross Yagi with right-hand circular polarization for receiving 137 MHz WX satellites like NOAA, Meteor, and even Orbcomm, if you so desire. Now, most people when they build antennas to receive NOAA or Meteor satellites, they like to build omnidirectional antennas so that they don't have to point them. Typical designs include the V-dipole for its simplicity, which lacks circular polarization and has a very omnidirectional pattern. Now, if you get it up high, you can get good results with the V-dipole, or if you elevation track to manipulate the radiation pattern to point at the satellite, defeating the purpose of having an omnidirectional antenna, you can also get pretty good results. But having circular polarization is a little bit of a step up. Many guides recommend things like this crosshair antenna, or they call it a turnstile here, with circular polarization, a quadrifilar helix or QFH antenna that also has circular polarization and an omnidirectional pattern. They discuss the V-dipole here. A double cross antenna, which is a series of crossed dipoles fed with phasing lines. That's another omnidirectional antenna that performs similarly to the QFH. Additional designs include the Lindenblad antenna. This one's rather complicated, but it's pretty popular for amateur radio satellite work. The egg beater antenna. This is the normal egg beater with circle loops and a very close reflector which forces the radiation pattern up to get a more omnidirectional pattern but above 20 to 30 degrees. Removing the reflectors will bring the pattern down a bit and you'll still get similar omnidirectional performance. These guys work very well and you could build one for 137 MHz. It should perform similar to the QFH. Or even the egg beater V2 is another antenna option. This antenna is the egg beater antenna except it has rectangular loops. And this reflector is very far from the rectangular loops. The reflector instead doesn't reflect up but pulls the radiation pattern down. This antenna has deep nulls in the top, so if you had very good line of sight and you got this thing up high, and you could still get good reception over the top with this antenna, the gain at low elevations is dramatically increased, so this would be a good performer for low satellite passes. In practice, I found it's the worst of both worlds. Now, did you understand there's a lot of omnidirectional antennas that could be used for this job? Why do I, in particular, want a directional antenna? First, I'm already standing outside and I'm already waving an antenna around. Why not get something I can point at the satellite instead of something that I stand there with idly? I think it's a lot more fun to actively track satellites and be able to point over there. Hey, there's that thing that I can't see that's sending down images of the Earth. And I'm pointing this thing at it and receiving a signal from it. And also, my backyard sucks for this kind of work. Here's a really low poly mesh of my backyard. I like to stand right here where our playground used to be. And you can see that I have trees up to the south that block up to like 30 degrees. And I have a house up to the north that again blocks up to like 30 degrees in the sky. So that's a pretty big problem. Now I do have good line of sight out to the east here. This isn't as good because these trees are on an angle, so these trees far down here do interfere with low glancing passes, and if you're a pass off that far to the east, you are a glancing pass. But to the west, I get my best results because this is a downward slope and the trees actually open up as opposed to close in on me. So, now you understand why I want a directional antenna, and why it's probably not overkill for my particular backyard if I want to stay in one place. Now, if I do grab my laptop and run around the house, I can make do with an omnidirectional antenna as long as I move to places where I actually have line of sight. But again, it just works that much better with a directional antenna. So now we know why I want one. How am I going to build one? Well, in the past I had built this 2 meter, 70 centimeter dual band cross Yagi here, which is not circular polarization for satellite work. And the 144 megahertz 2 meter side of this is based off of a video by KB9VBR on how to build the tape measure Yagi. Now, KB9VBR is not the designer of this antenna, but he does provide a pretty good write-up, gives a good parts list, and provides all the measurements, although he doesn't use metric, but hey, what do you expect? Freedom units, right? He provides the original source right down here. The original antenna was apparently published about in 1993 by WB2HOL. And this guy is breaking the laws of physics on his website. This number's wrong. This should be 7.3 dBi. We can check that with an online Yagi calculator real quick where we see we get 5.23 dBd. That's gain relative to the half-wave dipole antenna, which we know plus 2.15 will give us the gain relative to the theoretical isotropic antenna, which gives us that 7.3 figure. This is not DBD, it's DBI. That does bother me. I doubt he's going to fix it because the page is from 1993, but hey, one can hope. Also, some of these diagrams just aren't really useful. This has no scale whatsoever. We see there's a null in the back and there's a pattern out there, but I'm not sure what to do with this so much. His theoretical radiation pattern is a little more useful to us. We can figure out the 3 dB beam width from this. This is minus 10 dB down at the second circle here, which happens at the full 90 degrees. So if you try to estimate 3, you can see it probably lines up with his 50-degree figure for the his 67.5 degree figure. He says we're 3 dB down. So yeah, that's about 3, 60 degrees just there. That's useful. His diagram for the measurements is very well put together. And the really important design characteristic of this antenna is that it's super easy to match it to 50 ohms. Typically, Yagis match with, well, a variety of different types of matching networks, but they're not done with lumped elements or coax. They're done with these things called gamma matches or T matches. And basically what they are is you put a small metal element behind the feed point of the antenna, and that metal element becomes the actual feed point. And then it has sliding bars on one or both sides of it, and you slide the bars between those two elements to tune the input impedance so it is what you want. But this antenna was designed such that all you needed to do was add a short circuit stub, and you could match directly to 50 ohms. And then if you make that short circuit stub out of 300 ohm characteristic impedance twin lead, like this hairpin or beta match is effectively doing right here, well, that only takes 5 electrical degrees with a 300 ohm characteristic impedance, so it's very short, just a little wire right there, and you get a near perfect matching. I got 1.3 to 1 SWR on my first try, and that's just using the theoretical measurements directly into your build, which is pretty naive, and you should probably actually measure what the input impedance is before you try to make a matching network, provided you have the equipment. So now we've seen the source material for a tape measure Yagi. How am I going to make that circular polarization? Well, I went ahead and the first thing I did was, just draw 2 of these in, because when you want a circular polarized Yagi, you get 2 Yagis and you put them 90 degrees apart and then you phase them so that you get circular polarization correctly. So I just drew 2 of these into HFSS here, and then I scaled the measurements by my frequency versus the original design frequency. So these are the stainless steel material from the stock HFSS library. I drew a director, my 2 driven elements separately, and then a main reflector, and I copied that for the second Yagi there, and then I rotated them 90 degrees. Now everything in the simulation is defined from these variables: the driven length, tape measure width, reflector spacing, etc., and all these basic words, I converted the imperial measurements from KB9 VBRs right up to metric in millimeters, and then I multiplied them by the ratio of my frequencies, 146.5 over 137.5, noting that the original frequency is on the top of this ratio, even though that seems to defy dimensional analysis, because remember, it needs to be 1 over f over 1 over f, so that we have a longer wavelength at lower frequency here. So then I get all my new values, and there's only one measurement that was optimized by me as opposed to just scaled from the original design here, and that's the cross-pole spacing. And we'll get to why that is what it is in a little bit. But when I was initially starting out and I'm trying to figure out how to make a circular polarized Yagi, I know the general concept is to phase 2 Yagis that are placed in orthogonal directions to each other. I decided I'd go and I'd look at some commercial Yagi designs. So this one's by M2 Antennas. This thing probably costs a small fortune. Less than 1,000, I bet, but something ridiculous, so I wasn't going to buy this. Also too heavy to move with your hands, probably. You can see that they're using that T-match network that I talked about earlier. And you can see that they have, well, we could take a subset of this and just look at 3 elements here. So the ones with the T-match are the driven elements. Here's the one in the vertical, and here's the one in the horizontal. Now if we count the elements, we see we have a director, driven, reflector, and then that's the end of the vertical antenna here. And for the other antenna, we have director, director, driven, reflector. So the driven of the second antenna, the further back one, is behind the reflector of the first antenna. Now, I had no idea why that was at this time. I was like, well, why does the spacing need to be what it is? But I found this really good reference, which I'll leave linked in the description, that's about making circular polarized Yagis for amateur radio satellite work. So they start by describing what is circular polarization, how do you get it. They show the naive approach, which is to build a helical antenna. Now these guys work really well. They're not particularly difficult to match to. I actually wonder, and this is open question for anybody that wants to try it, if you build a VHF or a UHF, like 400 megahertz or 144 megahertz, ham radio bands, helical antenna, and you're operating it in axial mode, can you use an IB crazy wave trap match down at those frequencies? That would be an interesting experiment. The other option is, of course, the cross Yagi that we talked about. And now in this diagram here, these crosses look like they're right on top of each other. It's pretty difficult for me to tell, but it looks like the elements practically have no spacing between each other. So it turns out there's two ways to get the correct phasing between these, which is that you basically, if the E-fields are starting at the same place, as shown in this diagram, we see the E-fields hitting this plane right here, they should be 90 degrees out of phase, right? So if your antennas are right on top of each other and the derivative of each antenna is in the same spot, you need a 90-degree phasing line. But if you have some spacing, that might not be the case. So the other purest option to get circular polarization is to do a lambda over 4 spacing between your two driven elements. So in free space, this represents a 90-degree phase change, and you'll get the circular polarization. Whether you get right or left-hand circular polarization depends on how you connect the conductors to each of these. So basically, you could go ahead and try it in the simulator, if you don't want to have to think through it. And if you have the wrong circular polarization, you just flip the connection on one of these guys, and it'll change the relation of the phase, and you'll get the other circular polarization. Now, in my simulation, and based on their diagram, I'm not sure what their actual spacing was in this commercial Yagi, but with my driven element behind the other reflector, it's not a full quarter wave away. And if I made it a quarter wave away, the antenna would kind of be unwieldy, a little bit too long for my liking. Instead, I just went with what that spacing is, and I had to figure out what that was in terms of the actual phase change in free space. So that's a pretty simple calculation. Our wavelength is 2.18 meters, and we're 0.27, so 0.27, because it's 270 millimeters is the variable in the simulation, 2.18, and then we know that we get 180 degrees every 0.5, so we'll go ahead and multiply that by 180 degrees and divide by 0.5, and we see that's a 44.5 degree phase change, which is effectively 45 degrees. So in my simulation, what I'm going to be doing here is I'm going to be phasing my two excitations 45 degrees electrically, and then the other 45 degrees of phase shift that I need comes from the spacing between these two. And again, that just comes from the variable here, which is called cross-pole spacing, and in my case is 270 millimeters in the negative direction. So about how to excite the antenna in HFSS. Drawing objects in HFSS is something you can find a lot of tutorials for. Understanding excitations and understanding how to phase excitations is not something you can find a bunch of tutorials on. So I'm going to go through that with you right here. So first things first, there are two types of excitations in antenna modeling programs, and those are lumped ports and wave ports, or at least those are your two primary types of excitations. Now, lumped port is what you want to use like 90% of the time. If you're doing simple antenna stuff and you're not dealing with waveguides, you want a lumped port, because you only have one mode that you're concerned about from your coax or whatever's feeding it. When you make a lumped port, you create a surface, and on that surface you draw this thing called an integration line. And that sounds scary and confusing, but it's really not that bad, and I just had to have a grad student actually tell me how to do it because I couldn't find out how to do it anywhere else. It's climbing Mount Stupid without knowing the right words to Google. But what this means is just think about the direction of the voltage potential. So if I'm feeding this, and my center conductor is to the right on this half of the Yagi, and my shield is to the left on this other half of the Yagi, what I do is my shield is ground, and I have a voltage on my center conductor. So positive to ground, and I draw my integration line. And that's all there is to it. Now, we'll have to pay attention to the direction of that line later when we're building the antenna, because we need to make sure the center conductor agrees so we get the right circular polarization out of it. You can see that port 2 is exactly the same with its setup, and the fact that this line starts on the left and goes to the right tells us which end has to be the center conductor relative to how we're looking at the whole antenna and the other port there. Now, for the phasing, you can't do it directly from these port declarations. Maybe you can do it from properties, but I haven't found a way to do it like that. You have to go up to the whole excitations category, and then you go to Edit Sources, and it'll ask you for a magnitude of the source and a phase. So that's what's important. I want port 1, which is the upper port, 45 degrees behind the first bit that's being driven here. So I get 45 degrees from free space, and then I add an additional 45 degree delay, and I have 90 degree phasing, exactly what I want. So once I had that, I could just go ahead and simulate it, right? Yes and no. I'm not sure exactly what caused this, but I had a lot of problems with convergence in this simulation. So convergence in HFSS is defined by this metric called delta S, or the magnitude of delta S, which describes the magnitude of the change in the S parameters matrix, or the S parameters themselves, and you define a maximum. The program defaults to 0.02, but I upped that to 0.1, and I'm getting about 0.07. So basically, when I ran this with the stock settings, you have a couple of options for solvers here. And the stock options are maximum refinement per pass 30%, order of basis functions first order, and direct solver, and 6 passes. Now, I was not able to get that to work. I kept the maximum refinement per pass. I had to go up to second order for my basis functions, and I ended up using the iterative solver with the stock relative residual value. I don't exactly know how to explain what all this stuff means, nor do I really know what it means myself, but the point is that it's converging and the results make sense, and they've agreed with my real-world results. So note that you might have to change settings to get this to converge. Then the settings are the same for the other guy, and I have 2 solution setups here because I want one of these to just give me the radiation pattern and the other computes the input impedances. It saves a little time if I just wanted to change something and look at the radiation pattern. So onto the solution results. Here's the gain pattern for right-hand circular polarization radiation in linear units. So this is 5.9 linear, which is going to end up being like 7.7 or 7.8 dB. Here it's 7.7 dB. And we can check front to back ratio real quick here. This is orange. This is minus 12.5 at the border between orange and this greenish yellow. This is probably like a 15 dB front to back ratio at least, maybe a little bit better. And that's consistent with the original tape measure Yagi design. If we go back to that, he says front to back is, well, greater than 50 dB. So we're not as good, but we're not really designing for front to back. This isn't a direction finding antenna, it's a satellite receiving antenna. For left-hand circular polarization, we should see practically nothing. This is the linear gain units, and we have gain of 0.3 at the maximum. So this is always losing. 1 would be 0 dB. If we look at that in dB, we'll see the maximum is minus 5.1 dB. So very good. We have almost total LHCP rejection. Not 20 dB of rejection everywhere, but at least 5 dB. That's good enough for what we'll be doing. We can also go ahead and look at the linear gain in the X direction and the Y direction. That should be close to half of the RHCP gain. Now remember when we looked at the linear RHCP gain, it was 5.9. So 3 is about half of that. We see the LY is 2.9 and the LX is 3.05. So it's not perfectly balanced, and that probably comes from the fact that it was 44.58 was the phase difference in free space, and I put a 45 degree phasing line. But we're not going to be able to be more accurate than that in manufacturing anyway. So I'm happy with that. That's pretty balanced between LX and LY, so we're not looking at crazy elliptical polarization. We're right-hand circular polarized dominant. We have gain 7.7 dB. So our actual performance will be, over an isotropic non-circular polarized antenna, we'll get 7.7 plus 3 is almost 10.7 dB over a isotropic linearly polarized antenna for receiving. So that's pretty cool. Now after I simulated the radiation pattern and got what I wanted in terms of design, which didn't require too much tweaking, just the cross-pole spacing a little bit to make everything fit, I needed the input impedance. So we can look at that on this S parameter chart right here. And this is actually in the same position on the S parameter chart as the other tape measure Yagi. So the input impedances didn't change too much. And this position is really great if you wanted to match to 50 ohms again, because all you need is that short circuit stub. You move along where my mouse is with a short circuit stub just like this, and you get to 50 ohms real quick. But we don't need to match to 50 ohms. We'll need to match to 100 ohms. And we'll go over why that is in a little bit. So then I made a rectangular Z parameter plot, and this allows me to read off the complex impedance directly here. So this is pretty useful for designing the actual matching networks. So now that we know the Z parameters and that our radiation pattern is correct, we need to design a matching network and a phasing harness for the antenna. We know that the phase between the two antennas needs to be 45 degrees electrically, at least that's what we're going to put in the phasing harness, because we get the other 45 degrees in free space. And we want the total input impedance of the whole thing, 50 ohms, so that we're matched to typical 50 ohm equipment. That's going to mean that each antenna has to be 100 ohms, because 100 in parallel with 100 gives you 50 ohms. Now, it's important that they're each 100 ohms and not some other combination that ultimately results in 50 ohm impedance. The reason for that is that if they're not both 100 ohms, then you have unequal power distribution between the antennas, and even though you have the phase right, one will be overpowering the other, so that will also give you some kind of elliptical polarization. It's a similar effect to having the phase incorrect. So how are we going to go about designing a matching network that meets those constraints? Well, step one is to match each antenna input impedance to 100 ohms. So to do that, I'm going to use the ADS Smith chart utility, because I'm pretty familiar with it. So first I go ahead and I set up the Smith chart utility. I'm setting the center frequency to 0.1375 gigahertz, which is 137.5 megahertz. I'm going to keep with Z0 is 50 ohms, but we're not going to be matching to the center of the chart anymore. We're going to be matching to 100 ohms, so it's going to be over here to the right. And then we have to define the source and load terminations. So right now I have in here the numbers for the Z22, which is 12.34 minus J, 22.35. And that's where we're going to be starting. We have to enable the terminations, complex impedance, you select from this drop-down. And the source termination is 100 ohms resistive. So you go ahead and apply that. And then it's only going to take two elements to do this match, but I'll delete these real quick and I'll show you first. So again, if we had a short circuit transmission line, we're going to have to get 50 ohms. That's pretty straightforward and we get a good match there. But that's not what we want. Instead, we want to match to that 100 ohms, and there's no way to get there with that simple short circuit transmission line because it's constrained to this circle. Also, an open circuit, if you've worked with Smith charts before, you'll know that this is constrained to this circle. So there's no way that we're getting over there with one element match of transmission lines like this. Now, there's other options than what I'm going to end up doing. There's a lumped element matching solution here that's a series capacitor that wasn't too bad. I think it was a value that I actually could get a hold of without too much difficulty. And then I could use an open circuit or a short circuit stub. Short circuit was shorter, I think. And we could get to the 100 ohm input impedance. But I didn't really want to use a lumped element because in this case, sourcing a 109 picofarad capacitor and being that precise with it was, a little difficult. They tend to sell them in like, oh, here's 100 picofarad, here's 10 picofarad, and what really is the precision there? And then also you have to consider the power rating. Now, if we use just pure coax instead, it'll have a better power rating. Not that we're trying to transmit with this, but if you had intended that, you would want to have transmission lines or something that could support high power, and certainly cheap ceramic capacitors aren't going to do that. So instead, going with the transmission line match, use a series transmission line here to hop up over to this part of the Smith chart, and then an open circuit stub line, and we can get our match. Now, we don't just have to use 50 ohm lines. In fact, this, if we use a 50 ohm line, has to be close to like 66 degrees. But if we increase the characteristic impedance of the line to 93 ohms, we can make the line significantly shorter, which will make the wiring easier. So now it only has to be 34 degrees. And then we could do a similar thing with this other line here, except that 50 ohms ends up being shorter. You can see if I convert this to 93 ohm line, it has to be longer, not shorter. So we'll keep with the 50 ohms there. So use a 93 ohm line, which is also what I'm going to be using for my phasing harness because it's close to 100 ohms. And we need 34 degrees of it, and then we use a stub line, we need 52 degrees of that, and that'll be an open circuit stub, and then at the input right here, output of this matching network, we have a 100 ohm impedance. So then I repeated the process for the other input impedance, which is 13.8 minus J 21.8. And it's a very similar process. I'm going to use the same matching network. Dimensions are just going to change very slightly. It's going to get a little bit longer, I think 1 degree to almost 35. And then this is going to go down to only being 50. So there we have almost 35 and almost 50. So I took those measurements and I put them into our favorite graphics creation program, Microsoft Paint. And this shows the two matching networks that get us to 100 ohms at these two black dots right here. Then we want to create a phasing line between them. We want to take 100 ohms and we want to keep it at 100 ohms. We will place these in parallel, but we want a 45-degree phase shift between the input to the front one and the input to the rear one. Now, I don't have a 100 ohm coax. I imagine that some actually 100 ohm coax must exist, but what's a lot more common is RG62, which has 93 ohm input impedance, and at least for our purposes, is close enough. So this will result in minimal impedance change as a result of using this line. What you should be familiar with, and if you're not, the rule is that if your load is the same as the characteristic impedance of the line, the impedance is not transformed by the line. So basically, if you're matched, you're in the center of the Smith chart, yeah, and if in general you go along a line that is the same normalization as your Smith chart, so in this case, I'll change this to 50 ohms real quick just so you can see the effect here. If you have a line that's the same impedance as your Smith chart, you're making a circle of reflection coefficient about the center. It's a perfect circle. If you use a different characteristic impedance, it's no longer a normal looking circle, or at least it's not a circle that's centered about the origin, but it's a circle centered about the origin if you use the right impedance here. And if you're at the origin already, that is, you're matched, then that circle has radius 0, so you stay where you are. Now, to demonstrate the point here, we have something that is, I'll renormalize the chart. So if we normalize to 100 ohms, and we're going to start at 100 ohms, and then we're going to take a 93, so we'll start at 100 ohms there. Enable, apply. So we have a chart normalized, we're at 100 ohms, and we're going to take a 93 ohm transmission line. This will result in a very minimal movement. There's a tiny little circle there. It's not exactly staying at the origin, but it's not a lot of movement. So that's why we want to use 93 ohm line and not 50 ohm line for this purpose. If we were to use 50 ohm line on this Smith chart with this normalization, it would move all over the place. So you have to manually set it, but you can see that that circle is much bigger, and we would have to deal with impedance transformations here, which we don't want to do. So this was the theoretical phasing harness. So now we have the theoretical phasing harness, the antenna, and the dimensions, and everything that we'll need to go ahead and build it. So here's an Excel chart of the relevant measurements that you're going to need to build the Yagi out of 1-inch tape measure, and the phasing harness over on the left along with the theoretical input impedances. Now, a word of caution, I would not recommend going and building this phase harness with the physical measurements that are in here. The input impedances did not line up exactly in the real world as they were in the simulation. As a result, the phasing harnesses with these lengths right here didn't work perfectly on the first go. And you also have to be careful about the length of coax outside of the actual coax shield when you strip the end. That does significantly affect the phasing harness and the matching networks. So in my construction, I ended up using ring connectors and 1/4-inch bolts and nuts to keep everything together, and that had a significant effect on the matching network. So you're going to have to be careful with that. I'll go over that process in more detail in the next video, but basically I ended up tuning both matching networks to 100 ohms and then combining them with a phasing line that was likely close enough to 45 degrees. So a combination of a couple things being different did cause some changes in the physical build, but this is the correct theoretical phasing harness. It's just that these velocity factors might not actually be 100% as in the spec sheet at this frequency, The input impedance probably wasn't exactly what was simulated. I did try and measure it, and I got slightly different results, but it's a pretty difficult measurement to make with the nano VNA, at least to get good results. And then the termination of the coax stubs with the ring connectors certainly has an effect on the matching network. So I'll go over the actual measurements for what I cut and ended up working, giving me at least a 2-to-1 SWR. I think I was able to get 1.6 at center frequency, and it performed very well in terms of receiving NOAA and meteors, so must be okay. Anyhow, if you like this video, please consider leaving a thumbs up and or subscribing for more content. Stay tuned for the next episode.